Good morning all. Today we are going to study about three-phase short transmission lines, effect of load power factor on regulation and efficiency, and the numerical problems associated with short transmission lines. We will begin with the three-phase short transmission lines. As all of you very well know that the transmission of electric power is always done using three-phase system due to the economical reasons. In this diagram, a three-phase balance load is being supplied by using a star-connected generator. Each conductor of the transmission system has line resistance of R and inductive reactance of XL. In order to make the calculations more simpler, the three-phase system is analyzed by considering single phase only. Hence, the expressions which we have obtained in our previous video session for regulation and efficiency in the case of a single phase system can be applied for the three-phase system also. Even though this three-phase balance load is being supplied by using this generator, that is this three-phase generator, for the analysis of the short transmission line, we will be taking only a single phase portion into consideration, and that single phase portion is indicated here. This diagram is same as that of the single phase system which we have studied in our previous video session. Next, we are going to see the effect of load power factor on percentage regulation. In our last video session, we have derived the relation for percentage voltage regulation under lagging power factor load, and we have obtained the relation as like this. Similarly, we can write the relation for percentage voltage regulation under leading power factor load condition. The only difference between these two relations are the plus sign over here will be substituted by minus sign here. So we can write the standard relation for percentage voltage regulation as IR cos phi r plus or minus IXL sin phi r divided by VR into 100. Plus sign will be used when the load is a lagging power factor load, and negative symbol will be used when the load is a leading power factor load. We have to see the effect of this cos phi r on the value of this percentage voltage regulation. In the case of lagging power factor load, always the value of this percentage voltage regulation will be positive, because the numerator consists of only positive terms. Similarly, in the case of unity power factor also, the value of percentage voltage regulation will be positive 1, because at the case of unity power factor, the value of cos phi r is 1 and the value of sin phi r is 0. So making suitable substitutions, we will be getting the value of percentage voltage regulation as a positive value. Now considering the case of leading power factor load. In the case of leading power factor load, the value of percentage voltage regulation will remain positive only if this first term in the numerator is greater than the second term in the numerator. That is, if the value of IR cos phi r is greater than the value of IXL sin phi r, then definitely the value of percentage voltage regulation will be a positive 1. From the basic relation of voltage regulation, that is voltage regulation is equal to Vs minus Vr divided by Vr into 100, we can say that when the value of percentage voltage regulation is positive, definitely the value of Vs will be greater than that of the value of Vr. Or we can say that the voltage at the receiving end will be definitely small than that of the voltage at the sending end. So percentage voltage regulation value will be positive not only in the case of lagging power factor load. This value can be positive in the case of unity power factor as well as in the case of leading power factor load. In the case of leading power factor load, the percentage voltage regulation's value will be positive only if the first term in the numerator is greater than that of the second term in the numerator. Now for analyzing the effect of cos phi r on the percentage voltage regulation value, we will be considering the value of I and VR as a constant one. Definitely you know that already the values of R and XL are constants. So if we are seeing in the case of lagging power factor load, if we are trying to reduce the value of this power factor, that is cos phi r, definitely the value of sin phi r goes on increasing. As the value of XL is generally greater than that of the value of R, even though when we are trying to reduce the value of cos phi r in the first term, the effect of sin phi r in the second term is more dominating one, since the value of XL is greater than that of the R. From this we can say that whenever we are trying to reduce the value of load power factor, the value of percentage voltage regulation goes on increasing. This is because when we attempt to reduce the value of this cos phi r, even though this whole term is getting reduced, this whole term goes on increasing, and the effect of this term is more dominating comparing with this term. So in overall effect, we can say that the value of percentage voltage regulation goes on increasing. Next, if we are trying to reduce the value of power factor in the case of leading power factor load, that is if we are trying to reduce the value of this cos phi r in this relation, just like what we mentioned before, in this case also the value of XL is greater than R. Since the second term's effect is more dominating one, the value of percentage voltage regulation which we will be obtaining here will be a negative term. So whenever we are trying to reduce the value of this cos phi r in this relation, our sin phi r goes on increasing, and the second term's effect is more dominating comparing with that of the first term, since the value of XL is greater than that of the R. The overall numerator term goes to more negative value. That is, the effective value of this numerator terms becomes more and more negative when we are trying to reduce the value of this power factor. Hence we can say that the value of percentage voltage regulation goes on reducing whenever we try to reduce the value of this power factor. This is a very important topic. If you know these relations, you will be able to obtain these conditions from these relations itself. So in the case of lagging power factor load, whenever we are trying to reduce the value of this power factor, the value of voltage regulation goes on increasing. Whereas in the case of leading power factor load, whenever we are trying to reduce the value of this power factor, the value of voltage regulation keeps on reducing. Since the value of voltage regulation in the case of leading power factor load is negative 1, it's very clear that from the basic relation of the voltage regulation, that is Vs minus Vr by Vr into 100, it becomes negative only when the value of Vr is greater than that of Vs. That is, in the case of leading power factor load, if the value of voltage regulation is negative 1, then definitely the voltage which will be received at the receiving end will be greater than that of the voltage which is being sent from the sending end. This phenomena will occur only in the case of leading power factor load. We have already mentioned before, in the case of leading power factor load, it's not always necessary to have negative value for this voltage regulation. This regulation can become positive also only on one condition: the first term in the numerator must be greater than that of the second term in the numerator. That point is very clearly mentioned here. When the load power factor is lagging and unity, at those conditions of load power factors, definitely the percentage voltage regulation is positive. Not only at these two conditions, even under leading load condition also this percentage voltage regulation becomes negative on one condition: the value of IR cos phi r must be greater than IXL sin phi r. So it's very clear that the positive values of voltage regulation can be achieved for lagging load, unity power factor load and leading loads, whereas negative value of voltage regulation can be achieved only in the case of leading power factor loads. Hope this concept is very clear for you now. Next, we are going to the effect of load power factor on efficiency. The relation for both single phase power and three-phase power is shown here. From both these relations, the relation for currents are written. So this is the case of single phase system, and this is the value of current in the case of three-phase system. In the case of three-phase system, the relation for power is 3 into V phase into I phase cos phi. So that particular relation is written here. From here, the relation for current is written as P by 3 VR cos phi r. So if you are trying to reduce the value of power factor in this relation, definitely the value of current will be large. This large value of current will result in large value of copper loss, that is I square R losses. Since when we are attempting to reduce the value of this power factor, as the value of current is getting increased, definitely the values of copper loss also gets increased. Since the losses are more, definitely the transmission efficiency will be reduced. So whenever we are trying to increase the value of power factor, the value of this current gets reduced. So the value of copper loss also gets reduced, and hence the overall transmission efficiency will be increased. Similarly, when we are attempting to reduce the value of this power factor, the value of I will get increased. Hence the value of copper loss also will be increased. So due to this, the overall transmission efficiency gets reduced. Next, we are going to see a numerical problem associated with short transmission line. In this problem, the system given is a single phase one, and it is delivering a load of 1100 kilowatt at 33 kV. That means the receiving end voltage magnitude is 33 kV, and the power which is being supplied to the load is 1100 kilowatt. So from this, at 0.8 power factor lagging is also mentioned. So from this parameters we will be able to determine the value of current which is flowing through this load. That is from the standard relation of power, that is Vi cos phi. In this case it will be VR IR cos phi R. So using that standard relation we will be able to find the current which is flowing through this load. The total resistance value and reactance values are given. You are asked to find the value of Vs and the value of sending end power factor, that is cos phi s, that is cosine of the angle between Vs and Is, and transmission efficiency. As you know, in the case of short transmission line, the value of Is and the value of IR both are one and the same, so we will be writing it as I only. As there are no branches in between them, the same current will be flowing through. That is the current which is being sent from the sending end will be the same current which will be flowing through the load at the receiving end. Whenever such problems are asked, you are supposed to draw the equivalent circuit diagram and the vector diagram associated with this. So it's very clear that you must know this vector diagram, then only you will be able to solve the problems associated with this. So just like what I have mentioned before, first we will be finding the value of line current. Line current can be easily find out from the standard relation of power, that is VR I cos phi R. So we got the value of line current. Cos phi R value is given, so from there we can easily obtain the value of sin phi R. For making the calculations more easier, we will be using the complex notation form to solve the problem. Since we have considered the VR as the reference vector 1, we can write VR as VR angle 0, which is actually 33 kilovolt. As this current vector is lagging the reference receiving end voltage vector, I can write this current I vector as I angle minus phi R, or I can write it as I cos phi R minus J I sin phi R. So I have written I here as I cos phi R minus J I sin phi R. So I have taken I common from here. The value of I we have determined. So making the substitution, we will be able to get the value of I. Now from this vector diagram, it's very clear that Vs is equal to VR plus Iz. Vector Vs is equal to vector VR plus Iz. Now making suitable substitutions for VR, vector I and vector Z, we will be able to obtain the value of Vs, from which we can write the magnitude of Vs as 33,709 volt. From the complex notation of this sending end voltage, we can get the value of angle alpha, which this vector Vs will be making with the reference vector VR. In order to get the value of alpha from this complex notation of Vs, we have to find tan inverse of imaginary part divided by the real part. This you have studied in your basic mathematics classes. So we will be able to fetch the value of alpha. From the power factor value, we will be able to get the value of phi r as cos inverse of 0.8. So after knowing the values of phi r and alpha, we can easily find the angle between Vs and I. Once if the values of angle between Vs and I is determined, we can easily find the sending end power factor by taking cosine of this whole angle, that is the sum of phi r and alpha. So in the next step, we are finding the whole angle phi s, that is phi r plus alpha. seems to be 37.29 degrees. And in the next step we have determined its power factor value as 0.7956 lagging one. Finally, you are asked to find the transmission efficiency. It's very clearly given that the power which is being delivered to the load is 1100 kilowatt. So we can find the power which is being sent from the sending end by adding this power with the total losses which are occurring in this transmission line. So the losses which are occurring in the transmission line is I square R. By making suitable substitutions, we will be able to find the line losses value. The power which is being delivered to the load is given in the problem itself. So by adding these two terms, we will be able to get the power which is being sent from the sending end. Now you can simply determine the value of transmission efficiency by making this suitable substitutions here, and you will be able to get the value of transmission efficiency as 98.44%. In the next problem, you are provided with a three-phase transmission line. The power which is being delivered to the load is 5000 kilowatt at 22 kilovolt at 0.8 power factor lagging. The value of RA and XL is also given. You are asked to determine the sending end voltage first. So first you have to determine the value of sending end voltage just like how we have determined in the previous problem, because we have clearly mentioned in the first slide that a three-phase transmission system will be analyzed in the same method as that of a single-phase system. So definitely you will be able to obtain the per phase sending end voltage if we are following the same steps just like we have seen in the previous problem, from which you can determine the value of line voltage by simply multiplying it with √3. Next you are asked to find the value of percentage regulation. Percentage regulation, you can find it in the same way as that of a single phase system. The value remains the same. You don't have to multiply it with √3 or anything like that. Similarly in the case of transmission efficiency also. This problem you have to solve it by yourself. With that we are completing today's session. Thank you.